Hello, everyone. This is Fengli Xiao from Beihang University. I'm going to present our visualization system, GeneticFlow, for scholar impact analysis. This is a joint work with my advisor. Scholars are the gravity center of academic world. Analyzing scholars' impact are essential for many real-world tasks such as academic award selection, tenure evaluation, and academic output inference. There are now two major methods for scholar impact analysis. The first depends on indicators, such as citation count, H-index, etc. These indicators are good for ranking, but not for detailed scientific impact analysis involving context. On the other hand, bibliographic networks have long been deployed to display academic information, such as paper lists for delineating career trajectory, co-authorship network for collaboration history comprehension, and co-citation network for emerging topic detection. However, very few of these visualization design focuses on scholar-centric academic impact analysis. To resolve the impact-oriented scholar profiling problem, we introduce GeneticFlow Analytics, or GF in short, which is described in more detail in our KDD full paper this year. GF constructs a self-citation graph for each individual scholar, which connects all his/her publications into a structured context. The framework is mainly composed of two algorithms: node profiling to expose core papers in the graph that represent one's own research idea, and edge profiling to detect the set of core extend type citation edges that represent the evolution of the scholar's scientific contribution. In more detail, the GF node profiling method identifies advisor-advisee relationships on papers published by the target scholar. The author order information is used to detect the core papers, which includes those with the scholar as the first author or the scholar's student as first author, to avoid issues with alphabetically ordered papers. A statistical method is used to detect and eliminate subfields in CS, where alphabetical authorship is heavily used. To find extend type citations for categories of raw features, including metadata of cited and citing papers, features extracted from their citation networks, temporal correlation measures, and content and lexical patterns from the citation context and full text, are engineered and evaluated for their significance in differentiating extend type and non-extend citations. 20 features are finally selected based on correlation analysis and significance tests. We finally adopt the extra tree model as the best classifier, because it achieves an F1 score of 0.6 for 6 in tenfold cross-validation test. To build GF profiles, we apply Microsoft Academic Graph Data, or IMG in short. IMG is the largest open academic data source, which offers most of the required data for GF profiling. In building the system for visualization scholars, we pick for primary fields of study in the MAG topic hierarchy related to visualization, which collectively cover almost all papers in the visualization field. With these papers as starting point, we further obtain all authors in the field, and all citation links associated with visualization papers are extracted from IMG. The statistics of the dataset are shown on the right. After building the dataset, we apply GF algorithms to obtain profiles of top 1,000 scholars in the field, ranked by their paper counts. The number of core papers for each scholar decreased to 43% of the full GF graph in average, and the number of extend type citations are estimated to be 45% of all citations, under a probability threshold of 0.4. Moreover, we found that the subtopics within the visualization field are not appropriately detected in IMG. We then apply the pre-trained BERT model to generate a new visualization topic list using title plus abs tracked info of each paper. After applying an additional clustering algorithm, 11 top-level topics are also identified, forming a two-level topic hierarchy. This is the overview of the GF visualization. The panel in the left summarizes the information of the scholar and the GF graph. The list of his co-authored papers are shown in the bottom right panel. A hierarchical graph visualization is presented in the main panel. To display the GF graph, where the y-axis corresponds to the paper publication year. Each node represents one paper published by the scholar, and the directed edges indicate self-citation relationship. The top right panel displays the distribution of these topics by similarity-based embedding, with the size of each topic circle indicating the topic intensity. The node fill color indicates the topic of corresponding paper. And on the left side of GF graph, we show a timed bar chart to display the distribution by the scholar's research topic over time. When a node is selected, more detailed information of the paper is shown in the rightmost panel, including the abstract and research topics. Users can also select an edge to study the citation context between two papers. We show the cases using GF visualization. First, on Professor Daniel Akim's GF profile, 2 stages are detected. The first stage is from 1995 to 2004, where his early years' work are highly influential. 2 noticeable topics are database visualization and multi-dimensional data visualization. In the second stage, his peak publication time from 2004 to 2013, the research focus shifted to information visualization on multiple data types. In another case, we study Professor Xiao Li's GF graph. We find that it is quite difficult to comprehend the full graph initially. Using the functionality of GF analytics, we extract the core papers, citations of her GF graph, and remove the survey papers which lack extend-type citation links. The resulting GF graph indicates that Professor Li focused on the text and document visualization topic from 2009 to 2016. In conclusion, we make the following contributions in this work. First, we propose a visualization method based on GF analytics for scholar impact analysis. Second, we have elaborated the topic generation and color mapping mechanism for the visualization field. Third, we open an online system implementation of GeneticFlow, as well as the benchmark dataset for the visualization research field. That's all for the talk. Thank you.